Come, little child. Want to learn everything about ones and zeros? That sounded funnier in my head. Regardless, the topic of this video is in fact very interesting, and although it seems very basic, it is extremely important. My goal is to ultimately teach you how computers think, how they have memory. Before that, I need to teach about flip-flops and latches. Before that, I need to teach about logic gates and Boolean algebra. Before that, I need to talk about our ones and zeros. I'm going to introduce a premise to you. Analog and digital. What is the difference between them? An analog quantity is one that has continuous values, while digital is something that has discrete values. By definition, it's very simple, but perhaps conceptually and when you first get introduced to this, what does it really mean? Let me show you a little graph. Orientating the whiteboard so the light is hopefully mostly out of the way. Let's grab a barometer that I've placed outside and I monitored it over a day. And I can get two different pieces of information. I can get analog data or digital. Here's how the difference would look like. As you can see, I have two graphs. I have an analog graph or digital. Each data point corresponds to a pressure value and a time of day. Now looking at these two pieces of information, and you can imagine that information has space. The more information you have, the more space it takes up. Which graph has more information? I'll give you a moment to think about it. But the answer is this one. A continuous line like this has so much detailed information, where it has increments between all data points. For example, let's say this is every hour, 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock. You have a data point for each time. You have discrete values. In that case, you can transfer about 24 data points. This guy has technically, if you want to argue about it, infinite amount of data points. It's impossible to transmit this as a continuous line. We can't be smart about how we transmit information, because we can do this, transmit less data points, we can be cheeky feckers, and after we've transmitted the data points, do that. Hopefully hinting towards some ideas or concepts here that you might be clicking with. So as you can see, digital is a lot easier to transfer, efficient and reliable, and it takes up less memory, less storage space. Digital electronic circuits and systems rely on two possible states, and from a primitive perspective, it depends on the voltage value. What kind of voltages can you have in two states? You can have a high, or you can have a low. Have a 1, or you can have a 0. Have on, or you could have off. These are the types of terminologies that we use to describe these states. I don't tend to use the term on and off because when you will be building logic gates and circuits, they're all on. They have to be. I rather stick to the terms high and low and 1 and 0. Because this is a two-state system, we call this binary, and the two digits are 0, 1. One of those binary digits, that 0 or 1, is called a bit. Hopefully, these are clicking in with some of the modern technology I've been exposed to. Thank you so much for telling me that low is 0 and high is 1. But what does that mean? Like, you just said that it's a voltage value. So what is the voltage value? And that is very dependent on what kind of TTLs we have, and quite literally what specific chips we're using. We're going to use the idea of positive logic with a range of parameters where a high is okay and a low is okay. Let me show you. I want you to look carefully at this graph. There's a lot of information here. Let's say I have a chip, a logic gate, and I know we're kind of jumping the gun, but it's a system that determines whether we're going to have a high or a low. But what is defined as high or low? Well, let's say it operates at 5 volts. And so we design our chip, we design our systems in a way that the voltage is between 3.5 and 5 volts, register that as a high. This is a 1. What if the voltage is between 0 and 1.2 volts? Well, anywhere in between that range, we will register that as a low, a 0. Now things get iffy. What if the voltage ends up between 1.2 and 3.5? That's extremely problematic. You don't know if it's going to be a 0 or a 1. In a chain of events, we need to make sure that all the zeros are zeros when they're meant to be and all ones are ones when they're meant to be. Otherwise, it's a cascade effect. An early signal of a 1 is actually a 0. It can mess up our whole system in future. We cannot allow our system to be in that unacceptable region because we can't predict whether the outcome will be a 0 or a 1. This is one of the technological limits of logic gates and systems. how many you can put into series and parallel, one after the other, because you are going to lose voltage or you are going to gain voltage accidentally along the way. So it's kind of interesting that we actually have an analog range of data, anywhere between 0 and 5 volts, but we digitize the outcome, 0 or 1, even though it can have a range of values. You might ask yourself, well, how do these signals come in? Well, we usually talk about it in terms of a waveform. And so this is what a high and a low looks like. It's quite literally a square wave, where the rising part is called the leading edge, or the rising edge. And the falling part here for the low part, is called the falling edge, or the trailing edge. You don't need to worry too much about the edges until later when we get to flip-flops, but it's just something to be mindful. And so we can now transmit digital signals in waveform. Ta-da! High, low, high, low, high, low, high, low, high, low. Now, we're going to do something interesting. We're going to zoom in. Let's zoom in on this wave right here. Does it actually look like that? Maybe you can guess by the hint of my voice. Nuh-uh. It doesn't actually look like this. When you zoom in, this is actually how it turns out. There's a lot going on. It takes some time for our square wave to rise to that value. And so we have something called rising time and falling time for it to fall back as well. Initially, when the voltage shoots up, it actually goes a bit above the value. We call this the overshoot. Then it tries to balance itself out. This is called the ringing effect. And then there's a little bit of a droop as it continues downwards. You can imagine as it begins to fall, it undershoots, then the ringing continues as well. How do we determine, well, what is going to be the square wave? In this case, what we say is by the time the wave reaches 50% of its height, by the time the wave falls 50% of this height, we will call that the width of the square wave. It's quite literally called the pulse width. Now I want you to start thinking about it. If we have a machine that's working at millions of hertz, maybe if you're a computer geek, you might be realizing some things here now. And so that means it transmits millions of these signals in 1 second, very, very fast. This might become a problem. If it takes this long for things to overshoot, to droop, to go back down, to solve the undershoot, and so on and so forth, how limited are we technologically to ensure that that continues to perform perfectly? Another little thought for you. Another thing I want to cover is the clock. And yes, it quite literally is kind of like what you think. A clock on a wall, and you see the arrows moving with every second, right? And that's exactly what we're going to use. If we're going to be transmitting information, let's say a bunch of ones and zeros. Let's say I transmit 1, 1, 1, 0, 1, 1. How do you determine the 3 ones initially? Because they go high and they stay high. But how long do they stay high determines how many bits of ones you actually got. We solve that. Well, we compare it to a clock. Let's say this is our clock. Complete 1 tick of the clock, it has to go up and it has to go down. This is 1 tick. Now I have a data signal coming in. And we said we have 3 ones, one after the other, right? 1, 2, 3. Low, high again, whatever happens afterwards. So our code becomes high, 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 high. This is how we transmit data or information using a waveform. And you always have to have it synced up to a clock. Later, you will be talking about things like asynchronous and synchronous clocks. Generally speaking, we call these timing diagrams. You can have many. You can have data 1, data 2, data 3, data 4, all under the same clock. I've talked to you about the binary system, about bits, about how data can be transferred using waveforms. And now I'm going to show you a really cool sneak peek to anyone who's into computer science or gaming. Let's say we want to transmit our data, and I have 8 bits of data to transfer. The 1, 0, 1, 0, 1, 1, 1, 0. And I have data that I need to output, and I take in here. Think of a USB stick, okay? Shoving in my USB stick, and I'm sending it a bunch of 1s and 0s. How long will it take to transmit the data out into the data in, one after the other like this? Well, when we compare it to a clock, it'll take 8 ticks of the clock. Makes sense. 1, 0, 1, 0, 1, 1, 1, 0. 8 ticks. What if we could adapt or change our data output and data input ability, and instead of putting it serially, put it in parallel? What happens now? The numbers are still the same in the right order, 1 0 1 0 1 1 1 0. This guy is 8 times faster in transmitting the data than the serial input. And I used 8 bits on purpose because traditionally we use 16 bits, 32, and 64. Maybe a few things are clicking in for many of you now. This is a teaser and a prelude for a lot of things that are going to be coming up in our electronic devices and systems lessons. I covered a lot of terms before we even covered these things, but the problem with these lessons is that if I want to give bite-sized information, we're going to start talking about some abstract terms occasionally. But hopefully along the way, we fill in the gaps. If you have any questions, let me know. Happy physicsing!